Okay. For Chad, I just realized as I was turning on the recording, Chad has a physics test a week from today and a quantum test a week from yesterday. Good times, right? Yeah, so this is our next to last lecture before the test. I'll be reviewing next lecture, so this is just finishing up things from chapter 3. Chapter 3 was really about the math, just kind of reviewing what we've done and then looking at math things in quantum mechanics. So what we're going to be looking at today is the vector nature of quantum mechanics. So we've been finding solutions with things like psi as a function of x, right? And we found what I've been calling eigenstates for specific problems, like the particle in the box. We found that we had an infinite number of eigenstates, and we named them things like psi 1, psi 2, psi 3, etc., right? Where the subscripts were numbering, well, what was the difference in these states fundamentally? We were using the Schrodinger equation, so the Hamiltonian operator. So we were finding what states of what value? Energy. So those n's were labeling our energy states. Well, we learned further that to have a complete system, you have to have all of the possible vectors in the space, even if it's an infinite space. And they all had to be mutually orthogonal. And so we can put things into our spatial understanding to help us better get this. And so we thought of these like, let's say we had a system that only had psi 1, psi 2, psi 3, instead of an infinite number of states. And we saw something like that. We saw that we only had one state for the delta function, one bound state. And with the double delta, if we had done it, we would have found two bound states. So we could take if you had three states, we could say, well, that's the same as having x, y, and z. And any vector can be expressed as so much in the x direction plus so much in the y direction plus so much in the z direction. And so then we said we can have, we can start our system in any random combination we choose. Hence, we did the problem where we did the triangle starting for the particle in the box. And that's just going to be so much in state 1 plus so much in state 2 plus so much in state 3. Well, we're looking at that a little more carefully today. So one of the first things to recognize is that an operator acting on a wave function or a vector produces another wave function or another vector. It's kind of like, I'm going to go with the simplest operator of 5. 5 acting on an operator on a vector gives you a new vector that's 5 times larger than the original vector. Now you can have something more complicated that's going to change the direction as well. But the operator can change the direction, so change the relative amounts of the different unit vectors that are involved. And the unit vectors themselves are rather arbitrary. When we choose x, y, and z directions, I always do things like this, x, y, z, right? But what's to keep me from going x, y, z? Nothing. It's just we choose something that's convenient. And the same is true in quantum mechanics. We can choose rather arbitrary directions for our unit vectors, if you will, for our eigenvectors. And so we can do transformations between them. So the textbook actually starts out, section 3.6, starts out with something that I actually found a little useful. It says that, where is 3.6? I'm using the other textbook today because it's just organized a little nicer. Here's the difference in the new textbook and your textbook. The problems are color, so those are problems, whereas this is, and examples are in boxes, so this is an example worked out in the box. It's visually more appealing, I say. I'm going to stick with that. So it points out that if I want to find if I have vector A, then the component in the x direction is going to be I hat dot to the vector A. Right? By definition of a dot product, you're finding the parallel part. Well, in quantum mechanics, how do we do a dot product? We have two ways of writing it, one that's calculus and one that's not. Go ahead.
The inner product. So.
Okay, it's the inner product, right. So we would either put this as, and I'll put E sub I to say unit vector in the I direction. So we either do that, or we would do the integral over all space of whatever this E sub I function is and A dx, right? That's the way we've learned to do the inner product both ways.
So what's the E?
And actually, this should have been the E is just the state in the direction I. So it's the vector, unit vector I essentially is what it's supposed to mean.
Okay.
So we've learned those methods. They're the same thing, how you find a component. And so I have here a few things. A vector A can be written as a linear superposition of my unit vectors. And so the E's, I believe the E actually here stands for eigenstate. The eigenstates are my unit vectors. And so any vector can be made as a linear combination of those eigenvectors. And how do you get this relationship from this? It is a one-stepper. But it's important to recognize that that's just an expansion, really, of the whole process.
Dirichlet's theorem?
Well, this here is Dirichlet's theorem right there.
And then it's like the A sub n is taking the place of the C sub n that we had earlier?
Yes, yeah. But to get this second one to find what the components are, that was a second thing we shown with Dirichlet's. You just put E sub n acting on alpha, alpha, is equal to sum over A sub n. Oh, I should have put an M here. Got to make these different so I don't have a summation conflict. So now with this, the summation can come out, and A sub n is just a constant. But what is E sub m, E sub n? Bra E sub n, ket E sub n, by definition.
Either 0 or 1.
It's 0 if m is not equal to n, and 1 if it is. So it's A sub n. So that's the Dirac delta m sub n, mn. Is that right? My Dirac and Kronecker, I get confused still. Which then just is going to be A sub n. Actually, it would be A sub m the way I did it. It would be this one here. A sub m. But that's how it was arrived at. So, yeah, they used the summation over m and then put bra E sub n on it. So that's just showing linear combinations. Now, an operator, or we said an operator acting on a wave function gives you a new, or on a vector gives you a new vector. We can actually find a matrix representation for operators. So E sub m operator Q E sub n is QMN. Now you might look at this like I did and say, wait a minute, shouldn't Q operator acting on E sub n give me Q eigenvalue E sub n? Wasn't that our operator relationship? It is if you're acting on a function of the operator. But if E sub n is not an eigenstate of the operator, then it's not going to do that. And so QMN may be complicated or may be simple. If E sub n is an eigenstate of Q, then this QMN is going to be zeros unless m is equal to n. But if it's not, then you could have something different. Now, this here, Q operating on alpha, by definition, right, we said that alpha we would define as sum over n a sub n e sub n. So that's what has been done to make this. And we said that beta was defined as this. So if Q alpha gives me beta, then I'm going to have this relationship here. And if I close it with the E sub m on both sides, this summation over n and a sub n, that can be brought out. So you see that's brought out here. This here is the Q subscript mn. And so that's the left side. Sum over a sub n Q subscript mn. And then on the right-hand side, this here can be brought out because that doesn't have anything to do with those are just constants. And then E sub m, E sub n needs to be delta mn. And so that's why the right-hand side is B sub m. So we now have something that shows the B sub m's in terms of, now what are the B sub m's? The B sub m's were the transformation, they were the magnitudes of the unit, how much times this unit vector plus how much times this unit vector to get my state B. The A sub n's were likewise how much of this unit vector, how much of this unit vector to get state A. And those relate through the components of the matrix representing the operator. Now, up to this point, it's probably sounding really confusing, isn't it? So let's go ahead and do something to make it make more sense.
Can you go back 2 slides?
2 slides, yes.
Also, can you put up the past lectures tonight?
Yesterday's.
Yeah, okay, yeah. I was like, I thought I had them all up to date, at least as of Sunday. Yeah.
Think, yeah, but yesterday's.
Yeah. So you good?
Yeah.
Okay, so how do we actually make this useful? This here, by the way, this is called, I think it's the characteristic equation or something like that. This is a really important equation. And it comes just by saying, here's our eigenstate relationship. Operator at A acting on a function of the operator gives me eigenvalue A times that same function. And so I can take this and just subtract this from both sides, except for one thing. We said that using the vector idea, the operator, what is the operator in a vector idea? Operators are matrices. But this AN, the AN is a number. And so this here is supposed to be a unit vector. So that's 1, 0, 0, 0, 1, 0, or unit matrix, I mean, not vector. In 3 dimensions, it would be like this. Or in infinite dimensions, it would be like that, with 1s down the trace and 0s everywhere else. So that's what it means with that 1. And so if I multiply this by that unit vector, then I can subtract it across, and I get this equation. And this equation, like I said, it's the characteristic equation. It's super important to us, and I want it, well, we're going to have to see how it's important so we can do anything of use at all with it. So here is a more complicated example than we have in the textbook. Let's look at the textbook's example first, because example 3.8, which I'm looking in a different text to give you the page for. I'll just do that one first. So we have a system with only two states. So there's a two-state system. And notice we're using, these are normalized. What does it mean to be normalized?
All the probabilities add up to 1.
All the probabilities add up to 1. When using vectors, and I talked about this before, BRA1, you take it and you transform it. So that's BRA1. And so if I do BRA1 ket1, that's equal to 1, 0, 1, 0. And when you multiply these through, you take first rows and columns. This is only one row by one column, so I'm only going to have a 1 by 1, in other words, a single number for my answer. And I just multiply in sequence. So the first item in the first row by the first item in the first column, 1 times 1 is 1. The second item in the first row by the second item in the first column is 0, and that's equal to 1. So it's normalized. So these are both normalized eigenvectors. But then we have one more thing that's given to us in this problem. It says that we have the Hamiltonian is a vector with values hg, gh. And we want to find the eigenvalues. At this point, most reasonable people will look at this and say, okay, I have no idea what to do. Well, here's the first step. To find these eigenvalues, notice that if I have h acting on state 1, h acting on state 1, I'm going to have hg, gh, 1, 0. Using the same multiplication rules, I'm going to have h times 1 gives me h. And then I'll have g times, oops, I meant to change color there. That's as close as we're going to get. G times 0 gives me 0. So h plus 0 for the first row and first column. There's no second column, so I'm done with columns. I go to the second row, and for the second row, I'm going to have g with 1 plus h with 0. Well, that did not give me an eigenvalue situation. We don't have the same eigenstate coming back. So that means the eigenstate 1 is not an eigenstate of this operator. So we need to find what the eigenstates of this operator are, because the ones that we're given us are not. So we start by finding the eigenvalues. And as you know, you haven't done this before. It's not something you're supposed to be able to do right now because you've never done it. So I start with, just rewriting h is equal to is equal to that. And then we had that characteristic equation that was our H operator minus, and I learned to use lambda times the unit vector acting on whatever my eigenstate is. Is that. Now, how do we make that true is the question. And we make that true by writing out this matrix first of all. We write out that matrix, so my H, notice I expanded this for what I'm doing. Then we have minus lambda sub n times the unit vector. So that means I'm going to have minus lambda sub n here, minus 0 here because the unit vector is only 1 on the trace elements, 0 everywhere else. 0 here, minus 0 there.
Can you go over why it's 0 again?
Well, it comes back to this equation right here. This equation is the key of what we're trying to do. So we're trying to find that function n where my operator, in this case I'm using the Hamiltonian h, acting on the function n gives me my eigenvalue times the same function, same eigenvector. And this here was just rearranging, saying if I multiply this by the unit vector, then I can subtract it from both sides. So you notice this is subtracted, so it's 0 on this side. And here we have the unit vector times a sub n. And then, of course, f of n. So it's factored out.
Yeah, when you were doing your matrix, you said something about equaling 0 because...
Well, okay, so a unit matrix is 1 for all of the trace elements and 0 everywhere else. And so with what I was doing, I had, well, it was not 3, it's 2 by 2. But I have h minus 1 times my lambda n for this position. For this one, it was g minus 0 times lambda n, because the unit vector has 0 in that position. So coming to what we have here, let me write this with an intermediate step that hopefully will make it make more sense. So this is going to be h g g h minus lambda sub n 1 0 0 1. All of that so there I've expanded. The green is the lambda times the unit vector, or not unit vector, unit matrix. And the red is my Hamiltonian. And so then if I do my math with what's written there, I have h minus lambda n g and h minus lambda n. So do you understand how I got to this matrix now? It's really important to understand that step.
So when you're subtracting matrices from one another, you do the same thing that you did with the multiplication?
No, when you're adding or subtracting matrices, you just take the corresponding pieces.
Okay.
So this piece combined with this piece combined with this piece.
What if we had matrices that had different numbers of columns and rows?
You can't add them.
Okay.
Yeah, there's certain rules like that just like with multiplication of matrices, you have to have the same number of columns in the first one as you have rows in the second one to multiply. Now, for this equation to be true, it turns out that true if and only if the determinant of h minus lambda n, g, h minus lambda n is equal to 0. That's the only way it can be true. And so this gives us an equation we can solve. So I find the determinant. If it's a 2 by 2 matrix, how do you find the determinant? Two by twos are the easy ones. Yeah. You take the diagonal going down to the right minus the diagonal going down to the left. So in this case, I'm going to have h minus lambda n times h minus lambda n. That's the product of the diagonals going down to the right minus g times g equals 0. So let's solve this. First, expand this here. Well, actually, this is simple enough that I'm going to do it a different way. Normally, I would expand this and whatnot, but I have h minus lambda n quantity squared equals g squared. I'm just going to square root both sides. And so if I square root both sides, I have h minus lambda n equals plus or minus g. Remember, when you square root, you have two roots. And so if we solve this for lambda, I was technically correct, so I put minus plus g. There's nothing to say which one's which, so it doesn't matter. So we have two different eigenvalues here. We have lambda, and I'll call it A, I'll call it lambda plus. That makes life easy. Lambda plus equals h plus g, and lambda minus equals h minus g. What if we just found what is the lambda though?
Is it the unit vector or is it just
It was the eigenvalue. So I've just found the eigenvalues for this Hamiltonian operator. I don't have the eigenvectors yet, which is what I said I wanted to find, but I have the eigenvalues. So given this Hamiltonian h and g, I would have the eigenvalues are lambda plus is h plus g and lambda minus is h minus g. Now to find the eigenvectors, the vectors that make it an eigensystem. So I come back to my relationship. So I'm gonna rewrite everything. So there's my eigenvalues, there's my Hamiltonian, and I had that relationship that said Hamiltonian acting on F should give me lambda F. So now I'm just going to choose one. So using lambda plus, I'm going to have h f plus equals lambda plus f plus. I'm going to find what the eigenstate f plus is based on my eigenvalue lambda plus. So now I'm going to actually put in and for f plus, I'm just going to put A and B because I don't know what those are. I'm trying to find those. So A and B are what I'm solving for. And I put the same A and B for F plus again. Now, using my skills with linear algebra, you guys said you've neither taken linear, right? I take first element in the first column times the first element in the first row, or first element in the first row times first element in the first column. And so I have HA, and then second and second, plus GB. And then I go down to the second, and I'll have GA plus HB. So that's what I get when I multiply the left-hand side of my equal sign. Now we go to the right-hand side of the equal sign, and we have this is equal to, and this is easier multiplication. It's H plus G times A and H plus G times B. Now, this whole linear algebra is just a way of rewriting equations. This is two separate equations. Those two separate equations are HA plus GB equals HA plus GA, and GA plus HB equals HB plus GB. So I have two equations and two unknowns. If you have two equations, two unknowns, that's always enough to solve. Let's work our way through this. How would you solve for A?
Take the blue equation, cancel out the HAs.
Exactly. Then what? So you have B equals A. If you go to the second equation, it's going to give you the same outcome. That's actually part and parcel with how we got the eigenvalues. If that determinant is 0, you're going to have one equation is equivalent to all the rest combined. So if you only have two equations, they're equivalent to each other. So if we take the second equation, you notice we have the HB and HB we could subtract out, divide by G's, and we'd have A equals B again. And now you're like, wait, two equations, two unknowns. You said that was enough to solve, but they're redundant. It's really only one equation, two unknowns. But we have a third equation. That third equation is the demand for normalization. And so what we have right now is F plus is equal to, I'll put AA, right? Because A equals B. But that's not normalized. So to normalize it, notice when you put it in the broad, you do have to do the complex conjugates. So that's why I put A stars. Now we're going to restrict ourselves to the real case here, but so we have A mod squared plus A mod squared, or 2A mod squared. But that has to equal 1. And now we're down to stuff we've done many, many times. So I have A is equal to, and if you want to be technical, plus or minus the square root of 1/2. And if you want to be really technical, times e to the I theta, where theta is anything. But we always just say, let's let that equal 1, since theta could be anything. And so now I have my F plus. And I'm just going to take the positive sense. And you might say, wait, how do you get the last part? I got the last part by taking the original 1 and 2. 1 was 1, 0, and 2 was 0, 1. And if I take 1, 0 plus 0, 1, it gives me 1, 1. So now I have found one eigenvector and both eigenvalues. What remains is to find the other eigenvector. I can think of 2 ways to find the remaining eigenvector. If it's only a 2-state system, there's 2 ways. Otherwise, you just don't have one. One way would be to try to find a perpendicular to this. Another way, the way you usually do it, is to go through the same process with the other eigenvalue. So we'll go through the same process with the other eigenvalue. Whoops, I didn't put in enough pages to even finish this. One more page. So now I'm going to kind of let you guide me. So writing out our stuff again, H is equal to HG, GH, and our eigenvalue minus is equal to H minus G. And we have our relationship that HF minus equals lambda minus F minus. What should I do now?
I should write out a new matrix with H minus lambda.
Okay, that's what I assume you meant. I wrote out my matrix for the Hamiltonian, and for now this is my F minus. I still used A and G, or A and B. I could have used C and D. Here, let's use C and D. That way it doesn't look like I'm reusing things. They were just dummies, constants. So I wrote out the left side. What's the right side going to look like?
I guess I'm just confused by why the F minus is C and D, why it's a column.
If it's a ket, it's always a column vector. If it's a bra, it's always a row vector.
And why does it just have 2?
Because I have a number of reasons. We started with the 1, 0, 0, 1. We have a 2 by 2 Hamiltonian. You have to have the same number of rows as you have columns in the vector to even do this math. Your Hamiltonian actually has to be a square matrix.
So then your next matrix would be lambda 0.
Well, lambda minus is H minus G. And then what do I put for F minus?
CD.
Right. Now we multiply through. So when we multiply through, what do I get for the top row?
HC plus G.
Right. What about the bottom row?
GC plus H.
And on the other side?
HC minus G.
And below it?
HD minus G.
Once again, 2 separate equations. And once again, only one of them will be unique. So I don't need to write both of them.
Can you just go back up to when we multiply the right side of that equation?
Yes.
H minus G times the CD. Why didn't we get HC minus GD?
Okay, so this with this, right? And then this with this. Then we go down to the next row and we start over first column with first item. And then second column with second item.
What about the other side of the equation?
The other side of the equation, this is, I know it's in parentheses and it looks like it might be a matrix or a vector, but it's not. This was just a number. This was just a number. And so remember what I wrote before was, this is erasing ink, H minus G. It's not gonna work. What I wrote before was H minus G times C and H minus G times D. You expanded it out correctly. So since the equations are equivalent, I'm only going to write out one HC plus GD, that's a D, equals HC minus GC. Once again, Chad led us through before. We can just subtract the HCs from both sides. And we're left with GD equals minus GC. Divide both sides by G. And we have D equals minus C. So if D equals minus C, then I have, and I'll put C minus C. And now I have to normalize it again. How do you think this is going to normalize? Yeah, exactly like the other one. It's going to be C squared plus C squared. Well, C mod squared plus C mod squared equals 1. That is and so that means C is equal to plus or minus any random e to the I theta 1 over square root 2. And so we have our normalized F minus is equal to 1 over root 2 times 1 minus 1.
Where'd you get the 1 minus 1?
Because I found C is 1 over root 2. And so I put in 1 over root 2 here and minus 1 over root 2 here. Okay. Put in 1 over root 2 there and minus 1 over root 2 here. Then I just went ahead and factored out the 1 over root 2. So it was 1 and minus 1. Now you might be confused a little bit on one thing. How did I choose this one to be positive and this one to be negative? Why not this one negative and this one positive? Arbitrary decision. Either one's correct. They're different but correct.
Okay, then how did you get the, like for the F plus, you ended up getting 1 over 2 times ket 1 plus ket 2. I didn't understand that.
Okay, so let's do that with this as well. We had, I'm going to write these kind of smallish, which means I zoom in and write the normal size. Ket 1 equals 1, 0. Ket 2 equals 0, 1. So if I look at this, I have a 1 here. So I'm going to put a ket 1 to get a 1 there. And I have a minus 1 here. So I'm going to put minus ket 2 to get a minus 1 down there. So ket 1 minus ket 2 is equal to and so I got it by doing that construction. With something simple like this, you can do it in your head. With things more complicated, it may not be so easy to do it in your head.
So this is probably a lot. But why does ket 1 equal 1 over 0?
It was just given to us.
I didn't know if there's a formula.
No. It was given to us in the statement of the problem. So this could also be written as 1 over root 2 times ket 1 minus ket 2. Now, there's the last thing that remains to be tested. And I'm going to have to put in yet another page. And that is, are these two eigenstates orthogonal to each other? Should they be?
Yes.
Yes, they should. Our eigenstates need to be orthonormal. So I'm going to check f plus, f minus. That should be 0. So I have two ways of doing it. One is to make it 1 over root 2, 1, 1 times 1 over root 2, 1 minus 1. 1 over root 2 times 1 over root 2 is 1/2. 1 times 1 is 1. 1 times minus 1 is minus 1. And that's 0. The other way to do it would have been to say equals 1 over root 2 ket 1 plus ket 2, because I had rewritten it in terms of 1 and 2, times 1 over root 2, or that was bra 1 and bra 2, ket 1 and minus ket 2, which gives me 1/2 This way looked longer, huh? But what is 1, 1? And what is 2, 1? And what is 1, 2? And what is 2, 2? So we have 1 plus 0 plus 0 minus 1. That also shows that they're orthogonal to each other.
Okay, so these eigenstates, I'm a little confused because I thought that an operator was a matrix and then it gives an observable.
Mhm.
The eigenstate, which is what this ket f is, it also is a matrix and an eigenstate.
It's a vector, not a vector. Technically, is a one-dimensional matrix, but yeah, it's a vector.
Oh,
So, what we have done here, this whole problem, is what we did with our first particle in the box. Fundamentally, we had the Hamiltonian, and from that Hamiltonian, we found two things. We found the eigenvalues, the energy values, and we found the eigenstates. Here we had the operator, the Hamiltonian. They didn't have to give me the 1001, right? Because I didn't have to use that anywhere. I did because they gave it to me, but I didn't have to. They gave me the Hamiltonian, and from that Hamiltonian, I found the eigenvalues, and I found the eigenvectors. So here we did with matrix math, the same thing we did with calculus before. Of course, it was a different Hamiltonian. It wasn't the same Hamiltonian. So it's not, directly the same problem. But you see, once again, if you're given the operator, you can find its eigenstates and its eigenvalues. Now, we clearly don't have time to do this, but here's a 3x3. The first step is finding A operator minus lambda sub n times that unit vector, and saying that equal, doing the determinant of that and saying it equal to 0. So like I said, this here is the characteristic equation. Which is fundamentally doing for you what the Schrodinger equation did. So in this case, I would have minus lambda n 2, 0, 2 minus lambda n 0, 0, 0, 3 minus lambda n. The determinant of that is equal to 0. How do you find the determinant of a 3 by 3 matrix? No, okay. So it's important that I do this. You choose a row or a column of your choosing. And so I am going to, for a reason that will become obvious, choose this row. And then you take each element in that row. Whoops. So I'll take this element here, and I multiply it by the determinant of its co-matrix. The co-matrix is the matrix that remains when I take out that row and that column. Well, 0 multiplied by anything is 0, right? I chose one that had 2 zeros so that it would be simple for me. So you have equals 0 times the determinant of 2, 0 minus lambda n 0. Then you change the sign, so minus the second one. So here's my second one. Here's its co-matrix. So minus 0 times the determinant of minus lambda n 2, 2 minus lambda n. Flip the sign again, plus, but now I have 3 minus lambda n times the determinant of its co-matrix. Whoops, I screwed up in the middle one. The co-matrix, you take out the row and the column you're in, so it should have been 0, 0. It didn't make a difference for my answer, but it sure makes a difference for understanding how to do it. And so the co-matrix for the 3 minus lambda n is and so if I multiply that through, well, it's easier to not do that. So I have that. And that's going to be true if lambda n equals 3 or lambda n equals plus or minus 2. So we have 3 eigenvalues here. And then I go through and I have to do for each one of these eigenvalues, put it back in and find the eigenvector that goes with that. And then I'm going to have to combine 2 of the 3 equations that I get to solve for now A, B, and C. Okay, so we're 3 minutes over. I will finish this in class tomorrow, and then I'll review for the exam.